Alright, hey, today we'll be talking about AP Calculus work and other applications. A lot of great examples to work on today, but basically work is force times distance. And since we're talking about something that could change over time, which could be distance or force, it just depends upon which one you're asking, okay? We're going to be doing the integral of from a to b of f dx, okay? And remember, f is your force, dx is your change in distance. So if you change your distance, you change your force as you go over it, okay? All right, let's take a look at an example problem. All right, so let's say we have a 25-meter rope with a mass of 4 kilograms per meter 4 kilograms per meter is dangling from the roof of a building. How much work is needed to pull the rope up to the top of the building? Okay. All right, so since 1 meter of the rope has a density of 4 kilograms, so 1 meter of rope equals 4 kilograms. Okay, that means the gravitational force per meter of rope is going to be 4 times 9.8, 4 kilograms times 9.8 meters per second squared. Okay, and that turns into 39.2 newtons. Okay. All right. Now, if we take a look at the rope and we divide into small sections, here, let's draw a picture. All right, let's divide into small sections of length delta y, each requiring a force of 19.6 times delta y. Okay, newtons to move it against gravity. If delta y is small, all of the pieces lifted up approximately the same distance y, so the work delta w done on this small piece is approximately equal to 19.6 times delta y, or 19.6 delta y newtons times y meters. So in other words, our work is going to be not 19.6, geez, 39.2 newtons. Okay, and it's going to be times the length of the rope. All right, so when we actually calculate it out, the integral should look like, all right, which is going to be 39.2y. Okay, we do the integral of it. Okay, so when we do the integral of it, it should be, oh gosh, let me see, we're going to divide by 2, so 39.2 divided by 2. So that should be 19.6, I was getting ahead of myself, y squared, okay, from 25, from 0, okay, from the starting point of where the rope was starting to be pulled up. Okay, alright, and so what I basically do is just plug that in. So it's going to be 19.6 times 25 squared. That's going to take a lot of force. So the actual work needed to do to move this rope up to the top of the building is 12,250 newtons of force, or newton meters. Okay, joules, if you want to get really technical. Okay. All right. Let's try another problem. Okay, so what we're going to do is calculate the work done in pumping 6 feet of liquid that weighs 1 pound per cubic foot from a tank in the shape of an inverted right circular cone whose diameter is 10 feet and whose height is 17 feet. So just to get the concept across, here's what the actual inverted cone looks like. And just imagine it is the cone. Okay. Okay, so we're dealing with 6 feet of liquid that we're working with, and we want to talk about each little disc, each slice. Okay, so let's take a look at the actual slice. So the slice should kind of look like a fulcrum. Okay, and this right here is going to be the width, which is ever changing because as you get down further down the cone, draining out of here, the width becomes smaller and smaller. Now we do know that also this is going to be delta y. Okay, as we work with it. So the volume of each slice is going to look, okay, so volume is going to be pi times the radius squared, which is going to be half of w squared times the change in height, which is going to be the height of the actual slice that we were talking about. So that should simplify to pi fourths times w squared dy. Okay, or not dy, delta y. Alright, so this is going to be the actual volume of the slice, so that's changing over time. Okay, so now what we want to do is calculate the distances it's traveling. So if you notice, okay, so now we actually have the volume of it. Okay, so now what we're going to do is find work, and work is force times distance. Okay, right, and so our formula is starting to look a lot better. So delta W is going to be our volume, which is pi fourths times W squared. And then it's going to be times that by the distance, which is going to be 10 minus y. And that's going to be delta y. There we go. And so it's beginning to look like this. So now what we're going to do is replace w in terms of y by using similar right triangle or similar triangles. Okay, which is w over y is going to equal 10 over 17. Okay. All right, so it's going to look like this. Okay, and so when we plug it in and get it ready for its actual formula, we're going to get this, which is this all set up. Okay, now when we square the 10 and the 17, we should get 100 over, oh gosh, I need to really memorize what this, it's 289, yeah. Okay, and then we kind of cross reduce. I just realized an error I made. It shouldn't be 10 minus y, it should be 17 minus y as we go down because of the actual height. I was paying attention to this 10 for some reason. Okay, now that everything works out, what we're going to do is we're going to go ahead and do the integration of this. This one should be a lot easier of working with it, but basically the derivative, and obviously I took out the constant just so we didn't have to deal with it. The derivative, or sorry, the integral of y squared times 17 minus y dy. Okay, and once you do that, you should get 244.59 Newton meters. Okay, which makes sense because it's not a huge amount of liquid coming out, but that's the amount of work done by the liquid coming out. All right, and that's it for work and other applications. I'll talk to you later.